Tyler, what? Oh, boy. Well. So, well, he can watch the video. Perfect. So, on 15, is this the right number? Okay. The limit as x approaches a does not exist if. So pretty much for every one of these, it's more of a guess and check. If x is approaching 5, we typically would just plug in 5 for x. Well, x is approaching a, so we're going to plug in a for x. When you do that on the first one, you get a squared minus a squared over a, which is 0 over a. What does 0 over a simplify to? 0. So does that exist? It does. It's just 0. On the next one, if x is approaching a, you plug in a for x. You get, again, 0 over a, which is 0. 0 is a number. So yes, that one exists. On this one, if you plug in a for x, you get a squared over 2a. Which simplifies down to a over 2. So does that exist? Yes. On D, you get a squared over, if you plug in a, you're going to get a squared minus another a squared, which is a squared over 0. That does not exist because you're dividing by 0. Okay, Haley? Is this not the same one? There's a quiz review and there's a test review. Test. We're not at the test yet. Shoot. So you probably have a boatload of questions because there's stuff on that review sheet that we haven't even gotten to yet. Sorry. So the answer was this one where you divide by 0D.
If it was 0 over 0,
You'd have to factor cancel and then replug in. And if you still get something over 0, like a different number over 0 other than 0 over 0, that would constitute does not exist. Okay? Tyler, we just did 15. You want to pick another one? 17. Okay. So just like I said on the last one, if x is approaching 5, you would plug in 5 for x. So if x is approaching k, you would plug in k for x, which is going to be root k minus root k over k minus k, 0 over 0. So we have some work to do. We have to rationalize and hope that this manipulates itself out, because 0 over 0 is indeterminate. So if I take my fraction, root x minus root k over k minus x, and I rationalize by multiplying by the conjugate over itself, so that I'm multiplying by 1 to preserve the value, but change the appearance. My numerator is going to FOIL out to be x minus k. And my denominator I'm not going to distribute out because I wasn't rationalizing in the denominator. The rationalizing was for the purpose of the numerator. And by keeping that separate, it's also easier to see that x minus k and k minus x will become negative 1. Now I can reevaluate by plugging in k for x. So negative 1 over root k plus root k gives me negative 1 over 2 root k. Well, that's what you, and I knew that that would be hard because we've always done numbers. If x is approaching 5, don't you plug in 5 for x? So if x is approaching k, so anytime you do, this is just a good math strategy. Anytime you get to a type of a problem where there's an additional variable where you're used to seeing a number, back it up, throw a random number in there to like wrap your head around the process, and then go back into the one with that second variable, and now you'll have a clearer vision. Because we all do better with concrete numbers, there's no doubt. Other questions? Shaylin. Negative 1 over 2 root k, which is not there. So, why? Probably because it's not rationalized. Radical k over radical k is going to make that negative radical k over 2k. E. The calculus stuff does. Shaylin, 16 you said? So did you plug in 0? You got 0 over 0. So what manipulation technique did you try? If you did rationalize, right. So that cancels. And you just now plug in 0, and what do you get? 0. Yeah. Okay, so you're looking at a graph. This one's f of x, a piecewise function. This one's g of x, a piecewise function. Which of the following limit exists for these functions? Okay, so part of what's being tested are your properties, right? If you're looking for the limit of two functions being added together, our properties say that we can do those separately, that that's the same thing as the limit of f of x, and then separately the limit of g of x. Oops. And if you find those two limits individually and then add them together, it'll be the same answer. So that's what we're going to do. If you look at f of x and you focus in on 1, which is right here, what is the limit as x approaches 1? 1. Plus, you look at your g of x function at 1. What is the limit here as x approaches 1? Also 1. It's not the function value, but it is the limit. That is the intention of the graph, as it's getting closer and closer to that point, which has a y-coordinate of 1. So that one, it does exist. The answer would be 2. Not that they're asking you to take it that far, but it does exist. The second one is as you approach -2, and then we're multiplying these two. So the limit of your f of x function as you approach -2, and then we'll separately find the limit of your g of x function as you approach -2. So if you look at your f of x function and focus in at -2, what's the limit? .5-ish. It doesn't really matter because, again, they're not asking us for the value. They're just asking us, does it exist? Well, that one does exist. Times, as you approach -2 over on the g of x function, what's the limit? Does not exist. So if one of the two does not exist and you're trying to do multiplication with that, then the answer is does not exist. Sort of, until you get to division. Right. Division is always going to be a little bit trickier because even though they both exist, if the limit on the bottom is 0, you can't divide by 0. So it's a different reason, but it could happen. So limit as x approaches 0 of f of x, and we're going to divide that by the limit as x approaches 0 on g of x. So on the f of x function, what's happening as we approach 0? 1. On the g of x function, what's happening as we approach 0? 0. And of course, that does not exist for a different reason. So the only one that exists is option 1. So that correlates to the choice B. Kaylin? Okay. Did you plug in 3 right away? And it gave you what? 0 over 0. So our methods of manipulation are what? Did you factor? What did you do to the top? Okay, so what is that? Perfect. And the bottom? Okay. And what canceled? Okay, and that's it? Yeah. So then you reevaluated. And on the top, when you plug in 3, you get 9 plus 9 plus 9, which is 27. And on the denominator, you plug in 3. 3 plus 3 is 6 with a negative out in front, -6. It's okay. So this one's still going to factor. in x squared plus 4x squared minus 4? Did you do that? Did you further take x squared minus 4? And no, that one can't go further. And then the x minus 2's will cancel and you replug in 2. Tyler? Okay, so a function is continuous on an interval. So from A to B, it's continuous the entire time, including at A and at B. So if I come up with a random drawing, let A be there and B be there, and I draw something that satisfies that. It's continuous from A all the way to B, right? So there's B, there's A, and it's continuous the whole time in between, right? Yeah. There is a lot to get through with this one because there's a lot of notation, which is pretty new to us, so it's overwhelming. But part A, and we'll just kind of answer these as true or false. Function f is continuous on the interval from A to B. The only difference is this one was continuous on the closed interval, which means it's also continuous at each endpoint, versus this one says it's just continuous in between. Is that true or false? True. If it's continuous on the whole thing, including the endpoints, well then it's definitely continuous in between the two endpoints. So that one's a true. This one says the limit as you approach A from the right, which is this direction, equals the function value at A. True. This one says the limit as you approach A, which would be whatever this number is, equals the limit as you approach B, which would be whatever this number is. Is that true or false? False. They don't have to start and end at the same point. Like I could have, they're awfully close in this one, but I could have just as easily just drawn something like this, where the limit as you approach A is -5, let's say, and the limit as you approach B is -10. They don't have to match on the two endpoints. There would be no reason for that. Could they? Sure. You could draw like a symmetrical parabola and make them match, but they don't have to. So that one's your false one, but just for the sake of sifting through some more notation as good practice. D says that our limit as we approach B from the left equals the function value at B. That's true. And E says for all C values that are elements of the interval from A to B. That pretty much means for any C number that's in between A and B. Anywhere in that interval. For any C number, the limit as you approach C is going to equal the function value of C. And that's true because that is the definition of being continuous at C. And we have to be continuous everywhere in between. Yes? No. If even one of those limits does not exist coming from one side, the whole thing does not exist. Doesn't matter if they both or does not exist. This is a great one. Again, with something that has an additional variable that we're not used to and don't like. This m value would typically be a number for you guys, yes? But at any rate, we are trying to determine the value of m plus b, neither of which we know, oh yeah, m and b, so that the limit of f of x has to exist. So the places where we're concerned that the limit might not exist are going to be at 1 and at 2. So if we want the limit to exist at 1, we need the limit as you approach from the left, which would be using this equation, and the limit as you approach from the right, which would be using this equation for 1. We want those to equal each other, yes? So the limit as x approaches 1 from the left needs to equal the limit as x approaches 1 from the right, if it's going to be an overall limit existing. So from the left, we plug into this equation. You plug in a 1. 3 times 1 squared is 3. And we're going to compare that to what happens if you approach 1 from the right. If I'm approaching 1 from the right, I need to plug in an x value of 1 here. what happens to mx plus b when I plug in an x value of 1? It's just m plus b. And that's what they asked for. What is the value of m plus b? It's 3. Now, it could be that they ask you for what is m specifically and what is b specifically, like numerically, which that wouldn't be enough information. But if we also write this to be continuous at 2, we would do the same thing. As you approach 2 from the left, that's 2m plus b. And as you approach from the right, that's 9. And then you could solve a system of equations to actually get the specific value of m and b. But because they just asked us for m plus b, we actually already have it. It's just 3. You'd still get that if you separately found m and separately found b and then added them together. You'd still get that if you didn't notice that, whoa, wait, I already have it. But there is a shorter way of doing that one because it just kind of shows up, luckily. Next. Shaylin? Nine is tricky, yeah. Because it's not the calculus that's tricky, it's the algebra that's tricky. So you try to plug in 0, you get 0 over 0. So what manipulation tactic would you try? Okay, so your options are factoring, rationalizing, or complex fractions. Yeah, because there is no radical to rationalize, so that's out. There is no complex fraction to clear, so that's out. The only option is factoring, and this numerator is the difference of a perfect cube and a perfect cube. It's harder to see and more complex because within the difference of perfect cubes, we have a binomial at work, but we'll follow the same steps. So the difference of perfect cubes factors into a binomial times a trinomial. This is your SOAP thing, if that helps you remember. Same, opposite, always positive. So same, opposite, always positive, if you want to get your signs lined up. But the binomial is always created by the cubed root of the first thing and the cubed root of the second thing. What is the cubed root of this? 1 plus h. And what is the cubed root of that? Just, yeah, we already took care of the sign issue. And then on the trinomial, we always take this first cube root and square it. So 1 plus h squared. I'll just do it out later if I have to. And then the product of the two of them gives you the middle term. So 1 times 1 plus h is just 1 plus h. Which, if that was ever a minus sign, I would need to keep that in parentheses, but I don't necessarily have to with a plus sign there. And then the last term is this one squared, so 1. And again, it's all over h. So what happens is in your first, what usually you're used to as being a binomial, and it technically still is, it's just a binomial minus a number. So it's a binomial within the binomial. The 1 and the minus 1 cancel, leaving just h. And that just h cancels with your denominator, and now I can re-plug in 0 after that cancellation and get an answer. But the factoring, the algebra factoring in that one is what's the trickiest. It's not necessarily the calculus part. Jocelyn? Determine all the values of a. So again, we've got what normally we're used to having as a number is a letter. So that makes it complex. But we want to find all the values of a for which the limit as you approach 2 is going to equal the function value at 2. In other words, when the limit at a location equals the function value at the location, this is the definition of being continuous. So we want to make sure we find all the values of a for which this will be continuous. Continuity requires that f of 2, well, we're h here, I guess, requires that h of 2 equals the limit as as x approaches 2. So if we do the top two functions, What is h of 2? Actually, look at the whole thing. What is h of 2? Second equation. When you plug in an x of 2, what do you get? 2 plus a. The limit as you approach 2, we have to do double-sided. As you approach 2 from the left, you'd be plugging 2 in for your x in this equation, which gives you what? Yep. And on the denominator, you plug 2 as you're approaching from the right. You plug 2 in for x here, and you also get a squared minus 4. So we know that the limit is a squared minus 4, and we know we want that limit to equal the function value. So we just need to solve this quadratic. Solve for a. So you get a squared, you subtract your a over and subtract your 2 over. That gives us a minus 3 and a plus 2. So a equals 3 or a equals negative 2. And now that we have potential a values, you could be more concrete about it, and you could change that to like 9 minus x squared, x plus 3, and 9 minus 2x, and just confirm that it's continuous everywhere. So I guess technically with that in mind, you could work backwards via guessing and checking, but that would be a long process because you have to check every single one. And obviously there's a lot to check just at one number. Anything else? Do I want to? Yeah, we have a lot of time left. Mm-hmm. And what? It looked... Excuse me? No. I always give you all the practice questions I have access to. So split this up into like 16 and 16?
Well, no, because then I can do it by myself, and then know what I don't know how to do.
And then like try again?
Try and see if I
All right,
can.
in the future, do the odds and then do the evens. Well, that same thing would happen if I split it into 2 review sheets, silly. Thank you. So, 29 is more of a guess and check because you don't have the second function. It asks you, h of x will be continuous at -1, which is the obvious place we're interested in because that's where the jump occurs, when f of x equals what? So we pretty much have to guess and check on this one. So always on all of these, if we want it to be continuous, the limit as we approach -1 from the left needs to equal the limit as we approach -1 from the right. Well, the limit as we approach -1 from the left is using the top equation. So that's always going to be the same thing for every one of these options. If you're approaching -1 from the left, you're following this equation. So 3 times 1 is 3, 3 minus 2 is 1. So it's 1 for all of these as you approach from the left. We pretty much need to guess and check and see, okay, well, if this was the second function and we were approaching -1 from the right and plugged -1 into here, what would you get? -2. -1 cubed is -1. -1 minus 1. Nonetheless, it doesn't match. In this one, if we're approaching -1 from the right, you'd use this equation. -1 plus 1 is 0. Sine of 0 is... So that's not right. -1 here. -1 plus 1 is 0. Cosine of 0 is 1. There's your answer. D is not going to work because if you plug -1 into that, you get 0. E is not going to work because if you plug -1 into that, you're going to get 1/4. That one has to be a guess and check. Because these are all the hypothetical second equations. And so if I'm approaching -1 from the right, I have to use each of those hypothetical equations to see if it matched this left limit, which I found was 1. That method will work with, yes, because it's rational. The only points of discontinuity are going to give you undefined. It doesn't have to be 0 over 0. It could be a number over 0. Well, I would factor in cancel, and I would, for myself, say, here's where my hole is, here's where my asymptotes are, and I know that it's a point in discontinuity at holes and asymptotes. So I would probably do it that way. So this says the limit as x approaches a. So if I'm approaching a from the left, Claire, what is my limit as I approach from the left? And what is my limit as I approach from the right? And so they match, so the answer is B. No. The limit can still exist for an open circle, and often does. If it's just a hole, it definitely, the limit still exists. The function value doesn't, or doesn't have to be the same thing in this case, because they both exist here. The function value is C. The limit value is B. Them not matching has to do with continuity. That's a step beyond the limit. Do you follow that? So if this is just the limit, a hole is totally fine. Really, our limits aren't going to exist on piecewise functions where one ends and one begins at a different spot. Anything else? Oh, good. It's another one with a missing variable. It's easier than what? Okay. So given a function f of x, which is a traditional quadratic function, nothing to write home about, and this g of x, which is a lot more complex because number one, it's a piecewise, and number two, it's a rational. What is the value of k that will make function f equivalent to function g? All right, so if I want to figure out what function g really is, I need to factor and cancel. And so the x plus 2 cancels, which makes sense as to why they're saying, okay, follow this rational function for everything but negative 2, because negative 2 would be undefined. But as soon as you get to negative 2, just go with this constant number, right? And this now look identical, which means the graph of f of x and the graph of g of x are going to be exactly the same, except for at that location of that hole. But because they're leaving k open for us, we can just plug that hole up. So where is the hole? If the hole is at negative 2, comma, you plug in negative 2, you get 4 plus 4 plus 4, which is 12. The hole's at negative 2, 12, so you would want k to be 12. So that even though this has a hole at negative 2, you immediately just plug that hole up, and now this whole equation is exactly the same as that equation. It's just a different way of writing it. You're thinking, which is good.
Yeah, no, I got that and everything, but I was thinking,
Well,
hard, but I think
could it? Yeah, because really, no, you're right. Because it doesn't ask us about limits. It doesn't ask us about. Yeah, you're right. We could, I mean, you could do this with any two functions. You could say if f of x equals, if you said f of x equals, yeah, if I did something like this, I could probably do it. And then g of x, write a g of x piecewise that would be exactly that. Well, x cubed does something like this. So I could write two separate quadratics. Have this one be for where x is greater than or equal to 0. Yeah, it would be really hard to come up with. Oh, I know one. Here's a good one. If f of x equals the absolute value of x, I could write a piecewise, because that just looks like this. I could let it be the equation negative x when x is less than 0, and just let it be positive x, so turning it into two linears when x is greater than or equal to 0. Those two functions would be the exact same. It is hard to come up with an example beyond something like absolute value, I think. I'd have to think about it, but with any whole now we could do it. Yeah. Yeah, I could come up with a different variation of that easily, but good? Anything else? Should I stop the video?
Oh, no, that was a good question.